What I'm going to talk about this morning is NCHRP Project 5113, which is a synthesis, load rating of bridges and culverts with missing or incomplete as-built information. And I want to acknowledge my co-investigators, Yvonne Tatar, one of our session moderators, and also David Wagner from the Florida Department of Transportation. So just a little background. Hang on one second. Get my slide advance going here. Okay. As many of you probably know, all bridges have to be load rated. Federal regulations require bridges to be inspected every 2 years and also to be load rated. And what that rating is basically a calculation, which is shown in the slide here, where the capacity of the bridge, you subtract the dead load and then you divide by the live load. And basically what it's doing is looking at the reserve capacity in the bridge for live loads. And that's done for moments, for shears, for reactions, and sometimes also stress in any location that is experiencing those kinds of member forces. If the rating factor is greater than 1, that's good. If it's less than 1, that's not so good. And that basically means that the bridge doesn't have the capacity to handle those live loads. That calculation is usually done theoretically using some kind of analysis. But the question comes when you don't have all the information that you need on the bridge to do that calculation. What if information is missing? What if plans for the bridge are missing? How do you do that load rating? Well, the AASHTO Manual for Bridge Evaluation provides some guidance to owners for how to do that, but it's really pretty basic. And ultimately, the recommendation is use engineering judgment. In many cases, if a bridge has been around for a long time, let's say 50 years, it shows no signs of deterioration, and it's handled the loads to date, then we can pretty much assume that it's doing okay, and the rating should probably be above 1. But if you don't have all the information, it really comes to how are you going to handle that. So the objective for the project was basically to determine the state of practice for how this is being handled by owners, how they handle load rating bridges and culverts with missing information. To simplify things, we just refer to them as BCMI. The approach is pretty straightforward, and this is typical for all NCHRP synthesis projects. It requires a literature review, a survey of DOTs, some follow-up interviews, and then development of case examples. So I'll step through those steps from the project. As far as the literature review goes, it turns out that research under the topic really started to pop up in the early 90s. And a lot of the research has really focused on NDT methods and technologies that could be used to assist in this problem, and also a lot of work devoted to how diagnostic and proof flow testing can be applied to load rate bridges where we're missing information. There were also a few other surveys that had been conducted, and those were part of our literature survey. So while a fair amount of research has been done, most of it really focused in these key areas, NDT and load testing. The final report, what we did was we provided a table like this, which really just pulled out what we saw as several of the key resources that owners or engineers could refer to if they wanted more information about this but didn't feel like going through all the literature. Some of them having to do with load testing, some of them having to do with NDT. As far as that goes, I'll refer to the very nice ACI document on non-destructive test methods for evaluation of concrete structures. Very nice resource. And a few others that really delved into deeply, applying some of these technologies to address the problem. Moving on to the survey, we developed a survey and sent that to all the state DOTs, and we had a very good response rate. We had a 92% response rate, which amounted to 46 DOTs responding, which was very good. What we saw, of course, we asked a lot of questions about, do they have bridges without information? How do they deal with this? What methods, what technologies, et cetera. What we found is that nearly all the states have some bridges where they're missing information. I think there was maybe only one state that responded that said they didn't have any bridges of this type. Asked them how many bridges or what fraction of their inventories did they have bridges that were missing information. And the range varied, but in the end, we were able to kind of provide a broad estimate of how many bridges across the country are missing information. And that runs probably between somewhere around, almost 60,000 to a little over 110,000 of the more than 600,000 bridges in the country are missing some information. The majority of those that are missing information are concrete bridges, reinforced, pre-stressed bridges, culverts. They make up the largest portion of bridges where there's missing information. And usually in those cases, it's missing plans, whether they're design plans or as-built plans. And of course, that means they're missing reinforcement details. Quantities of reinforcement, locations for pre-stress, tendon details, layouts, all those kinds of things are missing. There are other bridges, other types where information is missing, some kind of one-off type bridges like pontoon bridges and steel culverts, but the majority are concrete. We asked states what kind of NDT methods they use, and the top 5 that are being used are listed there: sounding, GPR, dye penetrant, profometer, infrared thermography. A lot of DOTs, they have or they are using NDT technologies. Many of them, though, that's being done by consultants and specialty services companies. The in-house forces, the NDT that they're doing, are the very basic things like sounding, dye penetrant, things like that. So a lot of that work does get farmed out. We also found that about half of the DOTs are doing some kind of diagnostic load testing, but a little less than 20% are doing proof load testing. If you're not familiar with the distinction between those types of tests, a diagnostic test is conducted with loads generally that are below the design loads, below the legal loads, and it's primarily being conducted to determine things like load distribution factors, bearing fixity, the effects of secondary members, things like that, and those results will then feed into an analysis or a model of the bridge to calibrate the bridge, and then that model would be used to do the load rating. Proof load testing is where you are applying loads up to the maximum loads that the bridge is expected to see due to the design loads, legal loads, permit loads. And so that's really taking the bridge up to the maximum load that it's ever likely to see and demonstrating that it performs well, that there's no nonlinearities in the response, et cetera. About 60% of the DOTs, when we asked them, is their procedure formalized? They said yes. And of those, about 3/4, they have a documented procedure. Many states are also responsible for load rating their non-state-owned bridges, and that can make up a sizable portion of their inventory. And what we learned is that in many cases, it's those non-state-owned bridges that are missing information. They seem to be kind of the more problematic ones in their inventory. It turns out there's a wide variation in how states handle this. But at the same time, we didn't hear a lot of complaints about it being a big problem for them. Now, the procedures, what we saw is that we could group them into 5 general areas. And those general areas we termed experience-based, field measurement and historical data, design load, rational evaluation, and field testing. Those are our approaches. So I'll quickly go through those. Experience-based is when just as it says, an engineer is using their experience and knowledge of how bridges behave to come up with a load rating. Field measurement, this is primarily used for timber and steel bridges. This is where they're going out and getting field measurements, perhaps coupons. Once they have that information, they can develop a model of the bridge and do the load rating. A rational evaluation method, this is where it's primarily based on the NBI condition rating of the bridge and where the state has established a priori the load ratings that they're going to use based on that NBI rating. This table is from Idaho's manual, and it shows that if a bridge is rated a 6, the inventory rating is going to be a 0.64, etc. The design load rating approach brings in a little bit more calculation to the effort, and this basically says, well, if the bridge is performing okay, we're going to say that its rating factor for the design load is equal to 1. We're going to assume that. From that, we're able to then determine what the capacity minus the dead load would be. And based on that, using ratios for other vehicles, we can determine the rating factors based on that. And then the final area is field testing. This is where states are using a full suite of NDT, diagnostic and proof load testing to assist with their load ratings. So these are the 5 different categories. It's not that states are exclusively using one method and not others. Many of them use all of them, or a handful of these different ones to handle their bridges. Moving on to the case examples that we've presented in the project final report. We received 24 examples from 14 different states, and from those we selected 7 cases to provide narratives and details on. You can see the 7 cases here. They cover all 5 of the areas that we have, and you can see that all of them, except for the one masonry arch, are concrete structures. So I'm not going to go through all of them. I'll just go through several of them. First, this pre-stressed concrete slab bridge. This was in California, built in 1968. That sheet that you see there is California's live load worksheet, where they're using the design load rating approach. And you see at the very top of the slide there, for the HS20 load, they're basically determining the design capacity minus dead load, and then that is used to determine the rating factors for the legal loads, for the permit vehicles, etc. If a bridge was built in, say, the 20s, and it was designed to, say, an H10 vehicle, that capacity is going to be much lower. Using it, we might find that some of these rating factors are below 1, and that's going to trigger an evaluation, a next step in that evaluation, you might say, that California has in their procedure to deal with that. The next example is a concrete T-beam. This was built in 1960. This is using the rational evaluation approach. So basically, the NBI condition rating for the bridge is a 4. That, going back to that table you saw earlier, that would say that the inventory rating is 0.33. Not only that, it says that the bridge has to be load restricted or load posted. And so the next step in the process for this bridge was to look at a collection of similar bridges for which there were plans and do a statistical analysis of the ratings for those bridges to come up with the final load posting for the structure. Here's an example of a masonry arch bridge in Massachusetts, built in 1901. They used the field measurement and historical data approach on this one. They did extensive evaluations and measurements in the field to determine how it was constructed, the stones that were used in its construction, and then ultimately they developed a model of the bridge, did analyses, and finally arrived at their load ratings based on the analysis. And the final example is a proof test of pre-stressed concrete slab units. This is in Florida. Florida has tremendous capabilities, in-house capabilities to do diagnostic and proof load testing, and they've used that for quite some time very effectively. Again, this is where the bridge was basically loaded to the maximum load that it would be expected to see for all design, legal, and permit vehicles. The test demonstrated linear response, and so the DOT was comfortable in assigning load ratings greater than 1 for this bridge. The sketch or the drawing down below shows the vehicle that they use. It's their own in-house vehicle, and they can apply some very large loads to their bridge using that vehicle. So to summarize, the project, it established the state of practice for load rating bridges and culverts with missing information. And we found that almost 20% of the bridges in the country are missing some information, and that provides a challenge for load rating. We saw that there's widely varying approaches, but there are some commonalities to them. The majority of these bridges are reinforced or pre-stressed, but states are using a variety of tools and experience to handle the problem. A couple of the gaps or areas for future research. One is possibly looking at comparing these different approaches for the same set or sample of bridges. How do they compare? Are they similar? Are they widely divergent? And if they are, is that a problem? Continued efforts in NDT for concrete structures, particularly pre-stressed structures. There's still questions and uncertainties when the owners and engineers are dealing with their pre-stressed structures where they don't have plans that show the tendon details, the layouts, the harping, those kinds of things. And also questions have arisen as far as the new super heavy vehicles that states need to consider now. So questions regarding that. So I want to acknowledge the National Academy and TRB for the support of the project, the 46 states that completed the survey and those that sat for our follow-up interviews, the examples that they provided, which was tremendous, and also our undergraduate research assistant, Sophia Rupp, who assisted with the project. And with that, I'll close, and I'm happy to take any questions that you have.